annual event. And so I did want to just say a little bit in recognition of our sponsor, Colonel Craig Souza, who endowed the professorship that makes all this possible. The endowed professorship, the Colonel Souza Endowed Professorship in Meteorology, celebrates and provides financial support to a deserving faculty member, which you certainly are, from across the university, who will research and present on the value of functional meteorology to the PSU community. The donor interprets functional meteorology as the use of meteorological information to support decision-making or add value to an automated process. So possible topics include research include how a meteorological education in any major or discipline can improve an individual's decision-making process throughout their career. So again, this is like any academic field. It's richer than it initially appears in terms of the ways it can infect and inflect the quality of your life. How meteorology impacts business strategy, which again, if we think about the state of our climate and what we all live through around the planet on a regular basis, this is real world consequential stuff. How to add meteorology to decision support algorithms, how to enhance the general public's understanding of meteorology and the impact it has on our day-to-day life. Colonel Souza credits his long, illustrious career as a meteorologist in the United States Air Force from the lessons he learned as an undergraduate right here at Plymouth State University. Upon earning a degree in atmospheric science, some colleagues of mine here in that area, in 1987, Colonel Souza joined the Air Force. Over his career, he was stationed around the globe from Baghdad to the Pentagon. And for his distinguished service, he was awarded dozens of medals, including Defense Superior Service, Bronze Star, and Purple Heart. It is Colonel Souza's desire to educate and cultivate awareness among PSU students, regardless of their major, of the value of the value of meteorology can have in their daily decision-making and in their lives and in their careers. So again, I want to acknowledge a great PSU alum who's given so much to us, and not just to us, to New Hampshire, to the country, to the world, the work he's done, and our gratitude to the Colonel. I'm sorry he's not with us today. It's one of the highlights. I know when I come to this talk, I'm going to get to visit with him, which is not always so. You'll go visit. I'll try and make it up to his house sometime soon. I understand there's construction. So wherever you are, thank you, Colonel Souza. As to the recipients, this is a 3-year professorship. This is both your second year and your penultimate year.
Yes.
Indeed. Okay. So last year I introduced Professor Miller and sang his praises, and I will do so again. And this year, of course, we expect a more exciting, more impactful, and yet even better and more intense talk than last year, as will be the expectation each year. So level up. Although we'll forgive him for being born in Connecticut, not long before I was born, so we are of the same ilk era, and we drank the same water in our youth, for better or for worse. Yeah, exactly. He's also, along the way, our commitment to lifelong learning, he's also earned an MBA while he's been here. Don't ever stop. So I'm always inspired by that. Prior to joining the faculty, Dr. Miller, he joined us in 2005. Before that, he was a meteorologist for the U.S. National Weather Service in Alaska, in Anchorage, and at UNH. He was an instructor as well. He's also, one of his interesting things that he does that I learned about, he's a certified consulting meteorologist who actually regularly goes into court and testifies at trials. Who thought that's what you do as a meteorologist? Very cool, but periodically it's crucial to a case that we have meteorological wisdom in attendance. So congratulations on that. I'll also say, putting my notes down for a minute, I know from firsthand experience, and the students in this room know, he's an absolutely spectacular and dedicated teacher. My son, who is now studying theoretical and mathematical physics at one of the best universities in the world, proud graduate of PSU and student of yours. And he always told his mother's here with me, he'd come home from a session with Sam, oh, it's great, I just wish it could go on all day. It was so much fun. I love it, excited. You energized him as you do all of his students. So Sam, thank you for everything you do for our community, for New Hampshire, for the country, but also for kids like mine. So thank you very much. Welcome.
I didn't know my degree was in weather broadcasting. It's made for radio. I don't know. Yeah, it was weather forecasting.
Winter forecasting,
Yeah,
not broadcasting?
Well, yeah.
I don't know.
Did we have a typo with the?
I don't know.
Oh, good.
I'm sure it was my mistake.
So the topic of today's discussion is how to make a weather forecast without using the farmer's almanac. Okay. So, but first, and he's not here, I like to put this up there. So why don't we give him a round of applause? Okay, so what do we do? So every so often it slips out that I work as a meteorologist. The first one I get is, oh, so do you follow space rocks, meteors? No, not really. Other people think I'm on TV, and as I said, I've never done TV, I've done radio. My mother thinks I do this. Society thinks I do that. I don't know what these think. What I think I do, and then what I really do, which is spend most of my time sitting with my nose in a computer screen. It didn't always work that way, but it's getting to be more and more just looking at computers. And it's not a great way to do it, in my opinion, because I'm a little bit of an old, tiny guy. But here's the basic problem. We have a very thin, non-viscous geophysical fluid held down to the surface of a rotating sphere by gravity. The sphere is being unevenly heated as a function of the time of day and the time of year by a thermonuclear furnace 100 million miles away. At about 4/100 millionths of 1% of the total output of the sun actually reaches the Earth, and half of that doesn't even get down at the surface. It just bounces off. So, and you want me to tell you what the temperature is going to be there 3 days from now? So, all right, so this is a pretty big problem. There's a lot of stuff going on here, and our knowledge of it is imperfect, which is always the case. We're getting better at it. I'm going to talk a little bit about some of these things. Okay, but let's talk about some of the background. Where does it start? It goes back a long way, and this is not necessarily a complete history. There's just a few bullet statements, with apologies to Wikipedia. Okay, so 3000 BC, entries in the Upanishads showed that these folks really understood the weather on the Indian subcontinent. It was pretty well understood. They didn't know how to forecast it, but they have a pretty good idea what was causing it. So that's 5,000 years ago. I'm sure there is knowledge that goes back farther than that. There just isn't any record of it. In 600 BC, a Greek meteorologist started issuing crop forecasts. I don't know how he made his forecast, but that's what he did. In 400 BC, Democritus began predicting changes in the weather, and he claimed that he could also predict other aspects of the future, probably by very different means. Hippocrates wrote a book called Airs, Water, and Places, which is the earliest known work to actually include a discussion of weather. In 350 BC, Aristotle wrote a book called Meteorology. The philosopher remembers that. I'm going to tell you, Nate, he got most of it wrong, okay?
Almost everything wrong, but he was right about everything, too.
He was right about everything, but wrong about almost everything at the same time. Okay, he was definitely wrong about the weather part. I have a copy of that on my desk, and I meant to bring it here. Okay, several years later, a general named Theophrastus wrote a book. Now, he was an interesting guy. I included some of this background in my PhD dissertation. He, as a boy, grew up in a fishing village on the Mediterranean coast. He understood the sea breeze. After studying at Aristotle's Stoic college, he went on to become an officer in the Greek military, and he actually won a battle because of his knowledge of the sea breeze. The Greeks were in longboats that were being manned by freemen, and they were using oars. They were small. He was fighting the Phoenician navy, which was populated by slaves, and these are really big boats, and they were far less maneuverable. So he waited inshore with the Phoenician navy and the much larger ships sitting out in the deeper water. And he said, okay, we're going to wait here, and we're going to draw them in, and then shortly after that, the sea breeze is going to kick in, and they're going to be helpless. And he got it right, and he won that battle because he correctly predicted the sea breeze. That actually inspired me to write my PhD dissertation on the same subject, and it's much more complicated than you think it might be. In 250 BC, Archimedes, I'm sure you're familiar with him, he began studying buoyancy, and that's really important in the atmosphere. Are we going to have a thunderstorm or just flat clouds? So that comes back a pretty long way. Some more ancient history, now in the current era. Pomponius, a geographer, he began formalizing a system for climate zones. He named things the torrid zone, the middle latitudes, and the frigid zone. And he thought that nobody could live in the torrid zone. So they knew that the world was round, but they thought they'd never be able to get to the other side of the world because they'd have to pass through this kind of flaming desert. So they didn't think they'd be able to get into the southern hemisphere. A Chinese philosopher, Wang Chong, was the first one that figured out, or at least wrote down, that rain comes from condensing water vapor, and that the vapor comes off the ground or off the surface of the ocean. Prior to that, they thought it was falling out of heaven. He said, nope, this is perfectly natural. You can see the water evaporating in the morning, and then in the afternoon it just starts raining. So we're just following one big cycle. He got that right. An Indian astronomer, mathematician, and astrologer, and I'm not even going to try to pronounce his name. He did writings. He published the name of that book over there, which I also can't pronounce. Clear evidence that they understood atmospheric processes. In particular, they understood the Indian monsoon. All right, in the 7th century, Kalidasa mentions the date of the onset of the southwest monsoon, and that's also in India. And he traces the path of monsoon clouds across the Indian subcontinent. Saint Isidore of Seville, he wrote about astronomy, cosmology, and meteorology. He, in his section on meteorology, talked about thunder, clouds, rainbows, and wind. And I know rainbows, Lourdes, has always been one of your particular interests, right? I still have the optics section from that atmospheric physics course, too. Okay, the 9th century, a Kurdish nationalist wrote a book he called the Book of Plants, and this was being used during the agricultural revolution in the Middle East. Describes the meteorological character of the sky, atmospheric phenomena such as wind, thunder, lightning, snow, and floods. This knowledge goes back a long way. Exactly the mechanisms that was causing it weren't understood really until several hundred years later. In the 10th century, Moore, another book about wind and vapor. In 1088, the Dream Pool Essays. I just like the name of that book. It's got a great name to it. Chinese scientist Shen Kuo, he writes vivid descriptions of tornadoes. So we have a lot of tornadoes in the United States, but geographically, China is in a very similar location. A large northern continent north of China and warm water to its south, the South China Sea. So it's very similar to the Gulf of Mexico and the eastern United States. In 1121, another Muslim scientist, he was actually a Byzantine Greek, he published the Book of Balance of Wisdom. And he started talking about hydrostatic balance. This is one of those other things you learn in physics or thermodynamics. It's about the tendency for things to move mostly in the horizontal and not in the vertical. It originally came out of studies of oceans, but it can be applied to the atmosphere with a certain amount of caution. In 1337, William Merle, the rector of Dribby, starts recording the first weather observations. He kept a diary that went on for about 7 or 8 years, and that's the earliest known record of continuous observations. Okay, in the 16th century,
The son of a South Korean or Korean king invented a standardized rate gauge. And so the king, being a king, said, I can use this to charge more taxes. So he put one out at everybody's house, and depending on the amount of rain, he says your taxes are going to be based on the rainfall you get at your house. More rain equals higher taxes. Leone Battista Alberti developed the first anemometer. This is used for measuring the wind speed. Leonardo da Vinci devised a hair hygrometer, literally made out of a piece of hair, for measuring humidity. This Russian person, whose name I will not try to massacre for you, wrote a prognostic estimation of the year 1483 in Rome, and he writes about weather forecastings, and he made the connection that climate has something to do with your latitude. Now that goes back a lot further than that, but he wrote it again, apparently independently. In the 17th century, Galileo developed something called a thermoscope to measure temperature. Prior to that, and still for a little while after that, there wasn't a good scale, but if he could tell if it was hot or cold. Evangelista Torricelli invented a mercury barometer. So this is a column of mercury in an upside down evacuated tube with the opening down into a pool of mercury. The weight of the atmosphere pushes down on the pool and forces the mercury up into the tube. So the heavier the atmosphere, the higher up in the tube the mercury goes. Blaise Pascal, for whom the pressure unit is named, discovers, or rediscovers, the ancient Greeks understood this, that atmospheric pressure decreases with height, and he deduced that at some point there must be a vacuum. The first guy to guess that there was such a thing as outer space. Ferdinand II de' Medici, he sponsored the first weather observing network and had a series of them all across the Mediterranean coast of southern Europe. Sir Christopher Wren invents a mechanical, self-employing tipping bucket rain gauge. We still use a descendant of that technology. We've got one on the roof of Boyd. Edmund Halley, whoop. Try that again. He identified solar heating as the cause of atmospheric motion, and that's the right answer. The air is unevenly heated. It gets direct sunlight at the equator, indirect sunlight at the poles, and that results in changes in atmospheric pressure, which then results in changes in the wind. Okay, in the 18th century, you've heard these two names, Mr. Fahrenheit and Mr. Celsius. The interesting thing about Celsius is that his original temperature scale had 100 being equal to the freezing temperature of water, I'm not making a mistake, and 0 being equal to the boiling temperature of water. Yes, strange. And so he presented this at a conference, and they said, well, that's my scale, take it or leave it. And they said, well, we're going to leave it. So instead, they invented something, and if you're, Nate, you probably remember this since we're about the same age, the centigrade scale. So they took Celsius and flipped it over. And then in 1970, in honor of Mr. Celsius, they said, oh, come on, this is just the Celsius scale. So they dropped the centigrade, right? Okay, George Hadley, this guy was not a professional scientist, he was a lawyer, he was a smart guy though, was trying to explain the trade winds. Why does the wind blow from east to west over the equator and up to roughly 30 degrees north and south of the equator? I can show you what his picture looked like. There it is. That was his explanation. It had to do with, again, the sun heating the equator, and so it gets hot, hot air rises, and only falls obliquely on the poles, cold air sinks. And he said, all right, I can explain only part of this. The wind should be blowing out of the north all the time, from the heavy air at the pole to the warm air at the equator. And he said, and that's wrong, because this is what it's really doing. Why? Well, he was not trained as a mathematician. It took a French mathematician to come up with the answer to that. Okay? He was trying to explain this, and obviously figured large during that time in Europe. Okay, in the 19th century now, there's a lot that went on in the 19th century. I'm just going to summarize this for you. Luke Howard, an English pharmacist, believe it or not, he named the clouds. As a pharmacist, he was trained in the use of Latin, and so he gave them all Latin names. In 1802, he published a book which, with some changes, relatively minor changes, has become what's known as the International Cloud Atlas. We still use Luke Howard's system for naming clouds. Words like cumulonimbus, right? Nimbus meaning rain, cumulo meaning to accumulate, to heap up. Those are tall thunderstorm clouds. Those all came from him. All right, Alexander von Humboldt, he published a global map of average temperature, which was the first real global climate analysis. I'm going to show you that picture in a minute. Heinrich Wilhelm Brands published the first synoptic weather maps. So synoptic, this is a word that comes from synopsis. So if you collect a bunch of weather observations across great distances, all taken at the same time and in the same way, you can put them on a large map. And they were calling that the synopsis of the weather. It's now understood that, well, synoptic has come to mean something on the scale of a continent, something between 2,000 and 10,000 kilometers. Let's see, Nicholas Carnot, another name, big name in physics going back a long way, did a lot of mathematical work, but he laid down the second law of thermodynamics, which is a law of entropy, but it really talks about the distribution of energy and how efficiently it can be moved around. We use his law to model thunderstorms. You can figure out how efficient a thunderstorm is at converting potential energy into kinetic energy, the rising updraft of a thunderstorm. Any guesses on how efficient it is? Between 0 and 100? What's your sense tell you? I know you know it. Nobody in thermal is allowed to answer this question, so somebody else. I'll ask the artist who's busily sketching me. How efficient is a thunderstorm at converting potential energy into kinetic energy? You think it's 10%? Huh? Okay, excellent. All right, so let me ask John Christ, who's sitting up. What do you think? Is it 10%, 50%, 90%? 70%? Anybody else want to take it? I know you know it. Yeah, oh, you said 70? No, 50. You say 50, 50, any higher or less than that? What do you think? Way more? Way less? The answer is about 25%. Okay, so it's not very, and that would be under really, really ideal conditions. That's the most efficient it can possibly be, and it's never really that efficient. That gives you like an upper edge. It's never going to be more than that. It really comes down to the difference between the temperature of the surface of the Earth and the temperature at the tropopoles, the top of the lowest layer. Okay, this guy here, Coriolis. He was an engineer, a physicist, a mathematician. He was studying rotation in machines. And towards the end of that century, people began to realize the same thing could be applied to the atmosphere. And so we now have this force called the Coriolis force. It's actually an acceleration. But it helps to explain why the wind doesn't blow straight from the north to the south all the time. And it can be used to explain about a lot of other things too. It applies to anything that's moving but is not attached to the surface of the Earth. Ocean currents, air, airplanes. If you don't account for Coriolis and you take off east from New York, you are not going to land in Europe. You're going to be in Africa. You have to account for this. Elias Loomis becomes the first person known to attempt to devise a theory of frontal zones. So this is one of these fundamental ideas, and it became known as the American School of Meteorology. All right, so this is Humboldt's map. And those lines are called isotherms, lines of equal temperature. They go mostly from east to west, but he noticed, for example, that this one kind of bulged up. So something to do with the land in Africa versus the water in the ocean. So he named these different regions, hot, warm, temperate, so forth and so on. Okay, Lucien Vitti invents the aneroid barometer. Okay, so before we had a mercury barometer, so what this does is it uses some springs and gears and wheels, and it reproduces what you can get with a column of mercury, except you can put this one, say, in an airplane if you want to. You don't have to take your mercury barometer up in an airplane to figure out your elevation. So it reproduces what the mercury would do. Von Helmholtz, anybody, you know who von Helmholtz is, right? There's a bunch of equations named after him. He published the definitive statement of the conservation of energy, which became known as the first law of thermodynamics. This one is so important, sometimes it's just called the first law. And what's it all about? It's the three basic kinds of mechanical energy. There's heat, there's internal energy, and there's work. And that's it. And we use that pretty heavily through thermo and throughout meteorology to understand how when you add heat to something, it starts moving faster. The Smithsonian Institution began to build a network of weather observing stations across the United States. They were at telegraph sites, which followed the railroad tracks. And so once a day, they had the telegraph operators go outside at the same time, take a weather observation, write down sky cover, wind, temperature, that kind of thing, and telegraph it back to Washington, D.C., where they were plotting it on synoptic maps. This French astronomer, Leverrier, shows that a storm in the Black Sea could have been followed as it tracked across Europe if they had used telegraphs. So this is sort of the beginning of the idea, like, let's figure out where a storm is now, and we can figure out where it's going to be an hour from now or 2 or 3 hours from now, depending on the kind of storm. The U.S. Weather Bureau is founded, and we're getting up into the 1890s now. They began archiving data, so they kind of a precursor to what came to be known as the National Climatic Data Center. They started keeping these observations because they might come in handy for later. The U.S. Army Signal Corps issues its first hurricane warning. So this is 1885 or so, right shortly after the Civil War. All right, so there's a lot more that could go into this. I mean, it gets longer and longer and longer. I don't want to take up too much time on that. But here, I think, are the three most important things that came out of the 19th century. Number one, the growing conviction that the atmosphere is a physical object and behaves according to physical laws. It's governed by the same physical laws that govern everything else. Furthermore, they were far enough along scientifically to understand that those physical laws could be written in the language of mathematics, so that if we can solve certain physics equations, we could make some guesses about what the atmosphere is going to do in the future. I think the intellectual idea, that leap, was probably the most important aspect that came out of the 19th century. What about the 20th century? Again, many, many, many people who were much smarter than me have made some enormous contributions in over 125 years since then. But again, just using an overview of that, what's the most important things? Remember I mentioned the American School of Meteorology? It was about air masses and fronts. It came out of the language of 19th century European wars. They imagined a front as being a place where two air masses clashed, like two armies meeting each other. And where they met, you had disturbed weather. So it turns out that that's the right answer in the lowest 10,000 feet or so of the atmosphere. Now the Norwegian school, it was a very different way of thinking about it, and they're also right. They were taking the German physics of waves and applying them to the atmosphere. And it made a number of very correct predictions. One is the existence of the polar jet stream. But according to them, you had waves that were interfering with each other constructively and destructively. So if you get them to add up, to interfere constructively, you'll get one really big wave where they're all adding up in just the right way, and that's where you'll have disturbed weather. And where they cancel each other out, one is going this way, the other one's going that way, so you get nothing in the middle. That's where you have quiet weather. And they're right from about 10,000 feet up. Now, here's how we got unification of that. In 1920, a bunch of Norwegians got on a ship and came over to Boston. They sat down with their American colleagues, and they put these ideas together. The understanding is the polar front, which exists on the surface of the Earth, gives rise to the polar jet stream. And the polar jet stream then makes the front move. That's the simplest version of this. They feed back on each other. And another way of thinking it is that they're both manifestations of the same thing, which goes all the way back to Halley and before, which is that the Earth is unevenly heated. It's colder near the poles and warmer near the equator. And so all of this ultimately comes out of that temperature difference. It's all driven by the sun. During World War II, there were several competing forces trying to develop radar, mostly for uses in wars. But they discovered by accident that there was a kind of noise that was showing up. They were trying to see airplanes in the dark. And they noticed that when it was raining, it was more difficult to see the airplane. And they said, that must be the weather. That must be rain causing that. So let's remember that until after the war. After the war, they brought a bunch of these back here. Some of them went to Birmingham, England. Some of them came here to MIT. And they started retuning these same old World War II radars to take what they had thought of as noise and turn that into signal. Let's see what we can learn about the weather. And by that, it means mostly rain. So that has been highly developed. For example, in the last 20 or 30 years, they've added Doppler capability. So not only can you see where the rain is, but you can tell if it's moving towards you or away from you. And if you can slice and dice it up into tiny little boxes, you can even find places where there's rotation, which obviously is an important thing to look for. Dual pole came along a little bit after that, really only about 2013 or so, but the technology had been available a lot longer than that. Why is dual pole great? Well, we get one slice through a raindrop in this dimension, another slice in that dimension. And I can tell the shape of the raindrop that way. And if I know the shape, I know how big it is. And if I know how big it is, then I've got a much better idea how hard it's raining over there versus if I just got one slice through it. Now, there's a lot more to it than that, but there's a lot of other derived kinds of things that come out of that, but we won't need to go into that. Okay, satellite applications, beginning with the Cold War. What happened in 1957? Starts with an S, it's a Russian word. Sputnik, yeah, that scared the heck out of everybody, okay? Sputnik was about this big. It lasted 22 days. That was the first artificial satellite. So we had to get into the game right away because the Russians had beaten us to it. So we started lobbing satellites up there too. It was kind of a comedy of errors at the beginning. They put the Air Force in charge of it and they kept blowing them up. They were retuning ICBMs, taking the nuke off the top and putting a TV camera on there instead. That was the first attempt to build a weather satellite. And obviously that's come a long way too. All right, and then I think the fourth one, which is, I don't even know how to rank these, but the use of digital computers. That goes back to the idea of solving physics equations to predict the future. That idea has been around a long time, but there was no way to do it in any practical terms because it took longer to solve the equations than it did for the weather to get there. If you worked on it without a computer, say a slide rule, for a week, you could forecast the future an hour in advance. And that was an hour in advance from a week ago. So you needed a fast computer. And this is the way it's done now, or one of the ways that it's done, is we put these equations into a computer, which are they're in the language of partial differential equations, right, Eric? Okay, and then we numerically integrate them because there's no analytical solution, right? So we crunch it out algebraically. And the idea is you want to make the model atmosphere run faster than the real atmosphere. And we can go out a couple of weeks now. It takes about 2.5 hours, I think, for them to run those things out. That's pretty good. Okay, so in all centuries, anybody that does what I do for a living is, oh, so you're wrong all the time and you still get paid, right? Okay, how forecasting is done. All right, again, here's the problem. To predict what's going to happen on a square mile of land area or anywhere on that planet, I've got to understand what's going on everywhere in the Northern Hemisphere. In order to be able to get even a square foot right there, if I want to know what it's going to look like there, let's say we're outside, a week from now or 2 days from now, I have to understand what's going on the other side of the world, the entire Northern Hemisphere. That implies a lot of observational ability, and there are. There are thousands of weather stations that are now mostly automated. We've got satellites, we've got radiosonde balloons, these are weather balloons. They go up and take recordings in the vertical. We've got radar, we've got aircraft. Most commercial jets now carry an onboard system that automatically takes weather observations and radios them back to ground via satellite link. Okay, so my first job in weather was observer. Mostly what I had to do was memorize Luke Howard's catalog. I had to know the names of clouds and how to recognize them. There's some more details that went into it, but that was a big part of it. Know what the clouds are. Okay, and then in 1984, I went to the Air Force's weather forecaster school. And I thought I was a pretty hotshot weather observer. I was 23 at the time. And then I thought I was a pretty hotshot weather forecaster. I don't think I quite appreciated the complexity of the problem. And one of the things I really like about weather is it has a tremendous ability to humble you. So whenever you think you're getting really, really smart, nature finds another way to outsmart you. The other thing I didn't quite appreciate about weather forecasting was the tremendous amount of information that you had to be able to take in and deal with on top of the responsibility for guarding basically an entire base from bad weather. So the phone, there was a radio, there were several phone lines, there was a pilot to ground radio that we had to answer. There were teletype machines, there were maps that were constantly updating. I had to know what was going on everywhere within 20 miles at least. I had to be able to put out advisories, warnings, watches. By the way, I better get my aviation forecast up there as well, and route forecast from one base to another. Well, let's see. This is what I looked like my first day on shift all by myself. It was not, I mean, all right, so here was the problem. Information overload and fear, okay? So my boss at the time, he sort of let me sit there with that for about 2 hours. And he came out and, you know, I think the same thing was going through his mind that was going through mine, which is, wow, this is really humbling. And that's good, because I don't want to think I'm smarter than I am. So he gave me some really good advice. He was a nice guy. He was a very good meteorologist. He said, all right, Sam, here's what you have to do. Figure out what the weather is now. Then figure out what's causing it. Then figure out how those causes, those forces at work, are going to change over time. And then figure out what it's going to produce back outside again. What are you going to see as a result of this? All right, so I've translated this into somewhat more detailed language, and this is what I teach. What is the sensible weather doing now? I'll tell you what that means in a minute. In other words, what do you see out the window? Is there anything you need to pay attention to right now before you dive deep into the meteorology theory? For example, you don't want to be thinking about the polar jet stream over Wisconsin and the thunderstorm on the other side of that hill coming straight towards campus or whatever you're responsible for. What are the large-scale forces at work? How are they going to change over time? And then, what would be the resulting changes in the large-scale forces as well as the regional forces, things like stability? What's that going to produce back outside the window again? So there's a lot there, and I can summarize this the following way. What we call weather is the face of the clock. That's what you can see and you can directly measure. You can experience. Temperature, relative humidity, wind speed, wind direction, that kind of thing. That's what you can personally experience. Meteorology is the next place you go. It's what's making the face of the clock move, the gears and the wheels that are hidden behind the face. So you're going to observe this. You're going to infer that by applying the laws of physics. And then you're going to get in there and just turn a few of those gears. And then you're going to go back over here again and see what the face of the clock says now. And you can do that in steps. And as you well know, some of the terms in those differential equations involve time. So that works like a kind of switch. You can get in there and turn that dial and look forward into the future. That's the basic idea. There's a lot of different ways of realizing that. All right, so these are the things you can detect. Temperature, humidity. Dew point is sort of derived, but it's related to humidity. What's the wind direction and speed? What's that doing? Is it raining? Is it foggy? Is it hazy? Is there thunder and lightning? And there are others. That's what you can directly observe. From there, what we have to do is then figure out the mechanisms that are causing that. Variations in atmospheric pressure, variations in temperature, how the wind moves warm and cold air around, how it does the same thing with moisture, water vapor in the air. Spin, well, we use the word vorticity, but the atmosphere contains a kind of spin, and if you are in an area where the spin is increasing, you should expect disturbed weather. And if you're in an area where the spin is decreasing or going in the wrong direction, things are going to start to quiet back down. Jet streams and jet streaks. A streak is a little blob of accelerated winds that's riding along the jet stream. Troughs and ridges, so waves in the atmosphere on very large scales. I'll show them to you. Places where air is slamming together, places where it's spreading apart. Air masses and fronts. There's that American School of Meteorology again. Most of the rest of this is Norwegian. Places where lows are going to form. We call that a region of cyclogenesis, and others. Okay, so question, what is the sensible weather doing now? Step one. All right, you go to a place like my webpage, and you're going to focus in on the weather observing part. Okay, so this area inside the box is how you do a kind of self-brief. It also helps to go up on the roof and just look around, because this is only looking in one direction, right? We have a couple of other webcams that we can use. Okay, so there's a picture. What do you see? I see overcast clouds. I can tell you what kind of clouds they are and how high they are. So something's causing that. This shows an evolution, how they're moving over time. Notice that they're getting lower and higher. There must be a reason for that as well. So I'm already starting to think about what's causing that. Okay, this shows the temperature on other variables that have been recorded at the airport, our little grass runway airport, Plymouth Municipal. And these are current values from whenever I took this snapshot sometime yesterday afternoon. Each one of these is changing over time. For example, notice that on this particular day, 12 noon, the temperature was 15 degrees colder than it was the previous day. Why? Something must be causing that. So there's lots of different possible answers. That cloud cover probably has something to do with it. This is how the amount of water vapor in the air has changed over a 24-hour period. Not as much. And it's just a little bit lower than it was the previous day. This is how the wind has changed over time. We don't have direction on here, but just speed. This is the steady wind speed. This is the gust. So notice that the wind is quieted down. That indicates that it's probably more stable on this particular day than it was the day before that. But there could be other causes as well. This is how the pressure has changed over time. So these are 24 hours. So before you start doing any big meteorology, you're already thinking, all right, what's causing this, what's causing that? Is this trend going to continue? And you have to start reasoning it out in your head. Start taking all these mechanisms into account. All right, this shows a summary, and this is at Plymouth Municipal Airport for an entire 24-hour period ending yesterday at about noon. We've got the temperature and the dew point across the top. Here where it says WX, these are weather symbols, light rain, moderate rain. So it shows you that during about 5 hours, it was raining there. This shows you how the pressure has changed over time. We've got cloud cover, wind direction, and speed, and here visibility in miles, and then down here are the cloud heights. And those are, the lower you go, the finer the resolution on the height. As you go up, it changes to thousands of feet. If you're down near the surface, it's hundreds of feet. Okay, so I've got 5 or 6 questions in my mind, and I've got some possible answers. I have to go check up on all these things now. Okay, I'm not just going to look at one station. This shows weather stations around the Northeast. This updates once an hour, and again, I can look at this and see several interesting things going on. For example, these winds over here are all out of the west, but over here I don't really have very much wind at all. Here I see clear evidence of a sea breeze, so that's another factor I'd have to think about. It's cloudy here, it's clear over here. It's raining there, but it isn't raining over here. So what's causing that? I'm just taking stock. The other thing I can do is look at a radar summary. So we've got about 135 automated radar systems in North America called WSR-88Ds. And this consists of information recorded by several of them. We put it together in a computer. And this is radar reflectivity. These are not clouds. This is where there's precipitation falling out of the sky. You can see it's obviously moving west to east. All right, so what's causing that? Why is it going that way and not the other way? I'm starting to put together a picture. I can also look at cloud cover. This is from a geostationary satellite. It's one of the geostationary operational environmental satellites. It starts out in infrared because it's dark, and then it switches over. And these flashes you see, there's additional information that's been added to this. There's something called the geostationary lightning mapper, so I can see where there are thunderstorms. I can also clearly make out clear areas and cloudy areas. Why is that band shaped up there? It's a long linear cloud feature. That's probably a front, but I have to follow up on that. All right, so I'm starting to get a pretty good idea. All right. This is stability. I'm going to go back to this guy. Come on back. There. This was recorded from a radiosonde balloon launched over in Gray, Maine, which is outside Portland. So once a day, twice a day, usually at 7 o'clock in the morning, daylight time, and 11 p.m. daylight time, they're going to go outside, not 11 p.m., 7 p.m. They're going to go outside, they're going to take a 1 kilogram helium balloon and attach a small object about the size of a pack of cards. And in there is a transmitter and several sensors. It also has a GPS. He's going to let go, and over the next 2 hours, it'll ascend all the way up to the top of the stratosphere, about 30 miles up. And as it goes up, it's going to beam back a lot of information that we can use. Temperature, dew point, and we have, this is a record of the wind. And you can see the wind near the surface of the Earth is really different than the wind aloft. So that's more information that I can use. And then I can calculate a whole bunch of things about this column of air. For example, how much energy, potential energy, is stored in that column of air that can be converted into kinetic energy, the energy of a thunderstorm updraft. I can figure out hail size, the strength of a downdraft. There's many, many different applications. That's a kind of calculator, and this is really the basis of an entire course that I teach. All right, so I've got a pretty good idea of what's going on right now. Now I'm going to ask this question. What do I need to do right now before I start thinking about days away? And so it usually involves this. The National Weather Service calls this situational awareness, but get your nowcast updated. What's causing the weather right now? What do you expect in the next couple of hours? Do you need advisories, warnings, or watches? Do you have to update the current forecast? So get all this together, and really, you should have done this all within about the first 10 minutes. Now you get to do the real work. Figure out what's causing it all. So far, it's all been weather. Now we're going to switch to meteorology. We're going to go to a different world, okay? What are the large-scale causes, all right? So I'm going to just show you that, come on, there. Those are the areas we're going to start looking at now. Instead of in the middle, we're going to go around to the sides, and we're going to start considering some of this other information, which is diagnostic in nature, okay? So this is what we have to, one of the things we have to explain. What's causing all these showers to come out of the southwest, advect towards the northeast, and while the whole line moves east? What's causing that? Why? Because it might be affecting my area in a couple of days. Here's something else I have to look at. Where are these clouds coming from? You can animate this as well. And this also has lightning data that's been mapped onto it as well. What's causing this line of thunderstorms across the Midwest? I'm up here. And remember last night we got some of these flashes, right? Okay, here's another way of looking at it. This is from a satellite, and what they're doing automatically is tagging a cloud and watching it move. And from there, they can figure out what the winds are doing over time. They can assign a height to it by the apparent temperature of the cloud top. So there are 3 different ranges, low, middle, and high. And so out here, where I don't have any weather balloons, or really very much of anything except some model data, this can be a tremendous help. But again, what's causing the wind, for example, to recurve around like that up into the northeast? This is what I have to explain. I've also got to explain that. What happens on the surface of the Earth is a symptom of what's happening through the whole depth of the atmosphere. The atmosphere is not a two-dimensional object. Understand that, I've got to understand at least what's going on in the lowest 10 miles of atmosphere around the entire world. Okay, this is a tool to explain it, a tool. That is a northern hemispheric projection at 200 millibars, 250 millibars, but that's the jet stream. And you see waves rippling around the Earth. At any one time, there's somewhere between roughly 4 to 7 or 8 of them. If there's a small number, they move backwards. If there's a large number, they move forward. They move towards the east if there's a large number of them. There's about 6 waves out there right now. All right, and these waves have consequences to what happens on the surface of the Earth. If there's a wave approaching, chances are you're going to be in disturbed weather. You're going to start getting rising motions. You're going to start getting low pressure, clouds, maybe thunderstorms. This is another tool that I have. This shows another way of looking at the jet stream. And you can see, maybe you don't know how to read these things, but these wind speeds in here are well over 100 miles an hour. And this is up at a height of roughly 10 miles or so. This is up near the top of the lowest layer of the atmosphere. Here's a great big wave right there. Here's the opposite of that's called a ridge of high pressure right there. All right, this is another way of looking at it. Now we're down to about, this is 500 millibars. This is about 18,000 feet over our heads. I can use this. This is a kind of a special layer because it's halfway through the mass of the atmosphere. But I can use this to figure out where warm air is moving, where cold air is moving, where I'm likely to see stretching or crashing together, where I'm likely to see strong vertical motion. Another way of thinking about that is this right here. Remember I said that there's something called spin in the atmosphere. And these colored areas show where there's positive spin. It's going this way. If you hold out your right hand, wrap your fingers this way, your thumb points up. So if it starts spinning faster in that direction, you're going to get more upward. Am I getting this right, Eric? Yep, okay. Giving me the thumbs up. All right. So if you see one of these colored areas, that's called vorticity, moving into your area, that means you're going to start seeing disturbed weather. Have you noticed that this is kind of in the same place where that big line of thunderstorms was? There's obviously a relationship between the two. Here's another tool. This is a place where 500 millibars is getting higher and places where it's getting lower. So another tool that I can use to figure out what the causes of things are. This one here, this is at 700 millibars. This is about 10,000 feet up. This is not cloud cover. This is relative humidity. And where you see these green numbers here, that's very moist atmosphere. That's where you're likely to find clouds. One of the ways you can find out if your computer models have got it right is compare that to a satellite picture. Is it getting the clouds in the right place? All right? This is yet another way of looking at it. Now, this is only 5,000 feet above sea level. Here, I'm moving warm and cold air around. I can use this to find fronts very nicely. All right? Here's more of that again. Let's go back to this diagram. I can see what's going on in the vertical. I can do all kinds of calculations. Is this atmosphere likely to blow up and make a big thunderstorm? What do you think? Probably not. That looks pretty stable to me. Unless I can get the temperature over to about there, and then it's going to take off. There's a lot of physics that goes into this. All right, here's another way to explain it. This is contoured values of a stability index. Where I've got very low numbers, we're going to get fireworks. Anything below 0. If you start seeing numbers here that are like -6, 7, -8, that means some pretty interesting weather is going to be occurring in that area. Here's yet another way of looking at it. This is contoured potential energy that has been integrated from the surface of the Earth up to the top of the troposphere. Where I see big numbers, this is called CAPE, by the way, convectively available potential energy, where I get big numbers. These are in the thousands. That's my mother calling. Should I take it? How do I make it stop? Hi, Mom. There, okay. I deliberately didn't bring my phone so that wouldn't happen. My phone is sitting on the other side of the campus All right. Where was I? Okay, here's another tool. This has been processed quite a bit, but this is an outlook for severe weather that comes from the Storm Prediction Center in Norman, Oklahoma. I've got a lot of tools to diagnose what's going on. This is from yesterday. Did we get it? How did we hit it? Yep, we got it last night, right? Okay, so now I can explain that. I put all these things together, and I can explain everything that I see on there. And what I'm most interested in is like what's going to happen in the next 24 hours, so this is my primary focus. But to understand what's going to happen right there in the middle of New Hampshire, I've got to go all the way out to global scale and then work my way back down. What's that called? The forecast funnel. Very good. I made those guys read something about that. Okay, so now I know what's going on now and what's causing it now. The next job is to figure out how those causes are going to change over time. So all that stuff with troughs and jets and all that, I got to move that around and let it evolve. There's a lot of different ways to do that. You can do it manually, old-timey, I call that, and numerical methods, okay? So that's an old-timey method, and I just gave a bunch of people in my synoptic class copies of this book, okay? So this comes down from a time when meteorology was much less dependent on computers. So people took these, analyzed upper air charts, surface charts, so forth and so on, and began developing empirical rules based on observation. We've noticed that if we're generating troughs in the lee of the Rockies, when a certain thing happens, that's the last trough in the series, for example. And they even have little features that look something like this. So you cut that out, put it on a piece of transparency paper, lay it down on top of your map, write down a bunch of numbers. And you could figure out what direction that feature was going to move and how fast it was moving. So that's called the grid method. I learned how to do it this way in the Air Force Weather Forecasting School in 1984 and promptly forgot most of it. Okay, so now let's get into the modern methods. So I'll go up here to the top of my webpage. All these are links to different kinds of forecasting tools. Okay, so this is what I call the newfangled method. This is a numerical model. These are not observations. So what's happened is we've taken data from all over the world, thousands of weather stations, weather balloons, everything we've got. We fed it into a computer, which regridded it onto a record. I deliberately did not bring no in. Okay. Is there a way to turn this? Here? This one? The date? That one? And then?
There's a focus button.
Yeah.
Click that.
Yeah.
And then
Do not disturb. See, I learned something important here today. Thank you very much. I guess I could have brought my phone. All right. So we take data from everywhere. We feed it into a computer. We regrid it. It's many levels deep. There are millions of grid points around the entire world. And then we apply the laws of physics taught by my colleague Eric Kelsey right there to what we figured out is going on in the world, and we can drive it forward in time. Okay, so this happens to be a forecast. Let me see, right here. This is a 12-hour forecast. So this is 12 hours from the time that the original observations were taken. All right, now this would be a 24-hour forecast, the same thing, a day later. You can see there's all that spin that I talked about up there, and spin's moving from west to east for the most part. This shows you where there's high relative humidity and therefore likely clouds. This shows you what the surface chart will look like, highs and lows and fronts, and this color fill is where it's raining. So that's called quantitative precipitation forecast. And you can take it forward, that's a 36-hour forecast. Here's a 48-hour forecast. So you think, well, how could you ever be wrong with such great detail? Okay, so we have a problem with uncertainty. This is something that is probably inescapable. So this is another way to access information. But I'm going to be interested in what's called a spaghetti plot. And in a minute, you're going to get an idea of why it's called that. So the source of uncertainty is the fact that we cannot measure every single molecule in the atmosphere. Weather stations are on average 50 to 100 miles apart, and so you've got to make some guesses about what's going on in between them, and there's no way to really get around that. You can quadruple the number of weather stations and it won't help. At some point, there will be a point of diminishing returns. So uncertainty starts out small, and over time, the uncertainty gets to be bigger than the signal. And so we want to figure out where that's occurring and how long it's going to take. How sure are we? So this spaghetti plot looks something like that. Okay, this happens to be a 24-hour forecast. These are all from the same thing. This is 1,008 millibars. What we've done is taken the same numerical model called the GFS, and we've run it 40 times. Some of them are only 20. I think this one's only 20 times. And we've tweaked it slightly. There's the operational version, then there's 19 more copies of it that is somewhat simplified. You put in different boundary conditions, slightly different initial conditions, and run it forward, and then we can start to see where we're sure of ourselves. So this one, that looks pretty good. All 20 models put that isobar in the same place. How do you like that? Okay. Well, it gets better. Let me show you. Okay. So that's 24 hours out. There's 36. Now see how it's starting to get sloppier? Okay. Here's 48 hours out. It's getting worse. All right. There's 60 hours out. And just for fun, I'm going to show you the 4.5-day forecast. There. Okay. So unfortunately, you know, if somebody calls me on the phone and say, can you tell me the temperature in Miami, Florida 3 weeks from now at 2 o'clock in the afternoon? I'll say, no, I can't do that. But I can give you a guess based on what it's been in Miami, Florida 3 weeks from now at 2 o'clock in the afternoon over the last 30 years. That's called climatology. If somebody ever asks me a question like that, that's the answer they're going to get. For the first day or so, I think I can outdo a numerical model. Between days 1 and 5, the model's probably better than I am. Beyond that, no, nothing's going to work right. There are other tricks you can use called ensembling, and you can maybe push it out to 2 weeks with a lot of uncertainty, but to get beyond that, no, can't do it. Okay, this is another way of thinking about it. This is called a short-range ensemble plume. And so instead of showing you a map, you pick a point on that map, and you find several different solutions for a given parameter. For example, this happens to be temperature. And the point that I chose is Laconia, because that's the closest one here. So the black is the average solution for these models. And this shows over here the model members, the ensemble members. And this shows you the range. So for example, we've got pretty high uncertainty right about in here. But further into the future, interestingly, the uncertainty gets smaller again. And then if you continue out, it gets larger again. So it isn't necessarily a clean function of time. Sometimes you have a better idea what it's going to do a day and a half from now than you do 12 hours from now. It really depends on a lot of different variables. Okay, so that was temperature. This happens to be CAPE. This is the amount of energy stored. And you can see it pretty well nailed it last night. We had high CAPE values, a lot of potential energy. And how long did the lightning go on? About 2 hours. So it got that about right, but a pretty big range in here. But it was probably somewhere about in here, somewhere 750 or 1,000. This one shows you the wind speed and the uncertainty of that as well. To be honest, the thing that we're the worst at is getting the rainfall amounts right. We can do everything better than that. Things like pressure, we can do a pretty good job on. But rainfall, we don't measure it very well. Radar doesn't help very much, and we can't forecast it very well, which is why you always hear snow 2 to 4, 2 to 7. Sometimes they'll give you a really wide range. Precipitation type is also something that's really hard to do, especially in complex terrain in the north. Okay, so we don't need this guy, okay? Forget Harvard's Almanac. They went out of business, didn't they? This was their last year. I thought they were closing down. Do you know when this started? Something like that. It was actually Ben Franklin that started it, right? It says it right on here, 1792. I should look more carefully at my own visual aids, right? Okay, so now you know what the future gears look like. What's it going to produce out the window? Okay, so this shows the National Weather Service page, and I'm just going to cut to the chase. Partly cloudy, chance of rain. All right, we had to do all that to get to partly cloudy, chance of rain with a certain degree of confidence. All right, and then there's more. You can get these hour-to-hour forecasts. Again, that's all based on those ensembles. Okay, so according to George, a great man. Hippie-dippy weatherman, right? Okay. All right, so let's have a little pop quiz. This came from the Farmer's Almanac, by the way. I found it on Ricardo's door, okay? All right, so what I'm going to give you is a word bank over here, and then the names of certain phobias, all right? And actually, these are fears, all right? So we're going to go through them one at a time, starting with the top line. Nephophobia, what's that the fear of? Who wants to make a guess? Don't be shy, it's all right. Hearing nothing? Okay, that's the fear of clouds. Okay, how about the next one? Antelophobia. I bet you that's auroraphobia. That one is easy. So what, any guesses? Okay, that's the fear of floods. Okay, hygrophobia. Dampness? And you win the cookie for today, okay? You get an extra cookie when we're done in here. Nebulophobia. Fog? Correct. All right, very good. Auroraphobia, what's this one? This has got to be Northern Lights. Pluviphobia. Rain? How did you know that? I didn't know that. Okay. Heliophobia. Huh? Yep. I can't even pronounce that one. Ellipsophobia, what's that one? It is hurricanes and tornadoes. Yes. Okay. Frigophobia. Cold, very good. You're never going to guess this one. You did guess it. Very good. Is it the Latin? Is that how you figured that out? Okay, you're cheating. You should have excluded anybody with. All right, so finally, that's the problem. In order to know what's going to happen on 1 square mile, I have to know what's happening everywhere. Okay? And once a year, we all get together. Last year, it was in Houston. Where's it going to be next year? Denver? It's in Denver, okay? So this is what we talk about when we get together. Thank you very much. Yeah? Yeah, go ahead.
So I have a very simple question. You're probably going to think this is ridiculous, but
I'll let them answer it then.
okay, guys, I want to know what pressures mean. So if you're looking at a low pressure and a high pressure, I understand when I took class, I understand that like high pressure is good weather, I take those like
Yeah.
done. What the heck is the pressure?
Pressure is defined as weight per unit area.
Wait for
Unit area. Okay? And weight is like pounds. Okay? Area is square inches. Pounds per square inch. So in some places the atmosphere is heavier than it is in others. Okay? And one of the reasons that pressure falls is there's something taking air out of there. And that's where the jet stream and things like divergence come in, sucks air up. And so the pressure falls, you start getting rising motion, water vapor condenses, clouds, rain, the works. And then for high pressure, there's something pumping air in. And that's where the jet stream is crashing together in the upper atmosphere. And you get sinking motion. And it piles up more and more weight on the surface of the earth. And the sinking air heats up as it goes towards higher pressure, gets squeezed together. Any liquid droplets evaporate, and they turn into an invisible gas called water vapor. You get clear skies. You're welcome. Yeah.
If our accuracy goes down so quickly after just 4 days, excuse me, what do you think the point of the 10-day forecast is?
Let's see. We are trying to make money on this enterprise, I think. I remember when the Weather Channel decided to start naming winter storms, too. That was another big controversy. They're doing a 90-day forecast now. I don't know where they're coming up with that, but it's got to be just straight climatology. Farmer's Almanac, right. Any other questions? Yeah.
What are the odds of it raining on the same day or same event? In this case, Beaver Jim, Edward, you.
I've never calculated those odds. I have no idea. I don't even know how I would calculate those odds. But I don't know. Go ahead.
You're the perfect man to answer that.
I don't know anything about sports. I know that the Patriots are a football game in Boston, a football team in Boston. That's the extent of it. Okay? So I can't answer. I'm sorry. I'm going to dodge your question too. Sorry, I can't help.
We need Reynolds here.
Who?
Reynolds.
Reynolds?
Scott Reynolds.
Oh, that's Scott Reynolds. Yeah. What about him?
Well, that question we need Scott.
Oh, is he a big football guy? He strikes me. He would be a big football guy. Yeah. Yeah, ask him, all right?
I was thinking about the air jam question and how lucky we were to be able to see the solar eclipse during April a couple of years ago, when typically we would be socked under with lots of clouds and lots of other parts of the country were. Does that brief amount of time in which solar energy is not reaching the Earth
Not as much, anyway.
affect the weather?
Yes, there's your man right there.
What kinds of weather effects would we see from the duration of the solar eclipse?
Falling temperature?
Obviously, you could feel that.
The obvious one, and then if you cut off the energy that's heating the ground, that's heating the air above it, and you don't have the energy to cause air to rise. Air, warm air isn't forming as robust. And so, especially during the 2017 eclipse, I went from Oregon across the country up to South Carolina. Right, that was in August, right, when the sun angle was pretty high. And lots of fair weather cumulus clouds pop up over the day. We saw wide swaths of cumulus clouds dissipate before underneath the path. Yeah. And a lot of people thought, oh no, there are a lot of clouds, we're not going to see it. It wasn't a surprise. Without the updraft keeping it going, it just collapses. And that updraft is being caused by a warm surface.
You know, I took a picture of cumulonimbus that day.
You could,
Yeah, like that. Driving back from North Carolina after the cruise. But the only time I could see cumulonimbus by myself.
oh, and there were no clouds around it?
Yeah.
Yeah, okay, yeah. Yeah,
What's your favorite kind of cloud? Or what's it?
I'm thinking of, okay, I'm not going to give the snarky answer, which you guys know what it would be. How about a cumulonimbus?
That's a thunderstorm?
Yes, that's the best one.
With or without anvil?
What?
With or without anvil?
Oh, anvil, it's got to have the anvil. Yeah.
Could you talk a little bit more about kind of your experience being able to go in and testify about the weather?
I'm having a hard time.
Testify.
Oh, yeah, consulting. All right, well, here's the short version. Let's say you slip and fall on the ice. They'll hire me to say it was icy. Okay? That's the short version. I've done other stuff. I've done car wrecks, airplane crashes. I've done leaky radomes. About half of them have been slip and fall. And the other half has been an interesting variety. I had one where a 90-pound little old lady was going through one of those rotating doors, and the wind grabbed it and whipped it around, and she got thrown out of there and landed on her knees on the sidewalk. So, yeah, that was pretty bad. I had one, a drunk driver killed a passenger. I was hired by the public defender to describe the weather at the time, and there was freezing drizzle. And so it was kind of like a perfect storm of stupidity. He was drunk, driving on freezing drizzle, and so there was ice-covered roads. Yeah, that was in Nashua. Let's see, I've dealt with a stolen helicopter. Yep. Which he then crashed. That was quite a case. The guy, he left it out in an ice storm in Connecticut. He borrowed it from his wealthy employers in Bow, flew it to Connecticut to go gambling, left it out in an ice storm, got a phone call the next morning early, we want to go see a show, bring the helicopter. They didn't know he was in Connecticut. So we tried to fly it back from Connecticut. And he was flying low over the trees and talking to his girlfriend on the cell phone. And at that point, the engine sucked in, it was a turbo helicopter, it sucked in some ice, flamed out, and he crashed. He crashed in somebody's backyard. They took him to the hospital. His girlfriend rushed to meet him there, and so did his wife. And so he got divorced, and then this guy had chutzpah. Then I don't even know how to describe it. He decided to sue his employers for $5 million. He didn't win. So that's the kind of thing I get to do. I've been involved in that kind of stuff since roughly 2008. The AMS has a whole program called Certified Consulting Meteorologists. And so that's a pretty tough credential to get. You have to really work for it. You have to pay a lot of money. There's an oral exam, a written exam. You have to submit some samples of your work, and then you have to keep up certain professional development points, which I've not been very good about doing recently, but I need to go in there and plug them all in. And it's like, okay, well, I did this many consulting jobs this year. I testified in court. The other fun one is to be debriefed by a lawyer in an office. What do they call that? Deposition. to get a deposition. And that's kind of like a cage match with a lawyer. They're nice about it, but it can be pretty tough. So that's about that. You get used to it after a while. You know, you stand up in front of enough groups like this and you're good to go. Yeah.
What would you say your favorite weather trend is?
Matthew. I'm going to pass on that. What, just come up? Yeah, okay, I'm getting the time to, yeah, we're over an hour, and we have snacks waiting out there. So do you really want to hear me drone on any longer than I've been talking? All right, thank you, everybody. Appreciate it.
Always fun, Sam. Thank you. Always a pleasure. Had to pay the bills. All of the bills were. Thank you.
No, he's